Good morning, good afternoon, or good evening to everybody with respect to the place in the world where you are. I'm Laura Nenzi, and in this tutorial I will talk about monitoring spatio-temporal property.
We have several examples of systems that are intrinsically spatial distributed, for which the spatial configuration should be taken into account when we study and analyze such system. We can see here some example. On the top left, we have a wireless sensor network. So where we have a number of sensors distributed in a space that collect some data and that can be connected to each other in some way. Then on the top right, we have a bike sharing system. So think about a number of bike station in a city where people can pick up or bring back some bikes. And on the bottom left, we have a cholera spread. The cholera is a waterborne disease, so this is the spread of a disease in a space. And on the bottom right, we have the Turing pattern. So the formation of patterns that are then stable in time. So then we can see on each of them some property that could be interesting to study, as for example, for the bike sharing system, you would like to have the bike always available in each station, or maybe if in a station there are no bikes, you would like to find a station that is at close to your station, so in a radius of no more than 50 meters, where you will find a bike. Or in the case of the spread of the cholera, you would like to check the spatial spread of the disease, and for example, this can be described by the property that after 10 time units there exists a location at a certain distance from location where I'm checking this property, where the number of infected individuals is more than 50. For the wireless sensor nectar, an important property is the reliability, and this can be described, for example, saying that we can always find a path of sensor such that all sensors have a battery level greater than 0.5. And in the last one, we can take one particular type of pattern as example, that are the spots, so the formation of spots. And this can be described in words as we have some regions with a very low density of a protein A, and these are surrounded by regions with a high level of protein B. So what we will see today or what we would like to ask is how we can specify such spatial-temporal behavior in a formal and human understandable language. And also when we have like the specification, how to monitor the onset efficiently.
In this tutorial, we will see a possibility to solve that issue, so a way to specify and check these properties using the spatio-temporal reach and escape logic, STREL. STREL is an extension of the signal-temporal logic with a number of spatial operators. In the first part of the tutorial, we will briefly recall the signal-temporal logic, and then we will define the input of STREL, so how we will describe the space model, and how is defined a spatio-temporal trajectory. In the second part, of the tutorial, we will discuss about the monitoring procedure, and then we will see the applicability of the logic to a number of scenarios. Let's start with the first part of the tutorial. All the examples that we have seen can go under the general umbrella of complex systems. Complex systems are systems with an heterogeneous number of entities that usually are has a nonlinear interaction between the component, and then means that usually the emergent behavior cannot be derived from the knowledge of the single entity. Furthermore, we see in our example shows also an homogeneous spatial distribution, and they are all large scale systems. So all this complexity of this system often limits the possibility to analyze them using exhaustive verification techniques, and some common approach consists instead in simulating their design with the, for example, different initial condition parameters and inputs, and then use a monitoring procedure to check the single trajectory. So instead, what we will see in this tutorial is not about model checking, but is about monitoring. So what is a monitoring algorithm? A monitoring procedure or algorithm permit to check the single trajectory. So given a specification as a temporal logic formula, and a simulation, a trajectory of a certain model, we check if this single trajectory satisfy or not the property, and this will be the result. A logic that is very suitable to specify and check property over simulation of system is the signal temporal logic. Signal temporal logic, with probably most of you will know, is a linear time temporal logic that extends the dense time semantics of the metric interval temporal logic with a set of atomic proposition. And these atomic propositions are inequality on the variable of the system. We can see here the syntax of STL. We have the true constant, the atomic proposition mu, the negation, the conjunction, and then the temporal operator until phi1 until in a time between in time interval I phi2. And then we can derive also other two operators, the eventually operator and the always operator, and the disjunction operator that can be derived from the conjunction. So what does it mean to do a specification with a temporal logic language? So we see here a very simple example. We have a simulation of epidemic system. So we have the evolution in time of the number of infected, recovered, and susceptible individuals. And for example, we want to ask if between 30 and 50 time units, the number of recovered individuals becomes more than 60. This can be described by this temporal logic formula, where this is the operator eventually, and this means eventually in a time between 30 and 50, the number of recovered individuals is more than 60. Similar, you can describe property with the always operator, where a property should be true in a certain time interval, and then you can use the until operator to say that phi1 should be true for a certain time interval until phi2 should be true in a time unit inside the interval I. The signal temporal logic has two semantics, a Boolean semantics that gives just a 0-1 answer. So a tells just if a trajectory satisfies or not a property, and also it has also quantitative semantics that can give a value of the satisfaction. Furthermore, the evaluation is done at each time step. So as a solution, you can have a Boolean signal for the Boolean semantics or a quantitative signal for the quantitative semantics. So we say that in the signal, we know that a certain time step t of the signal is so the signal at a certain time step t is equal to 1 if and only if the trajectory at the time t satisfy the formula. And similarly for the quantitative semantics, you have at each time step the value of the quantitative semantics with respect the trajectory at that time step. We call also the quantitative semantics the function that is computed is also called the robustness. So given a certain trajectory and a certain formula phi, we can compute a Boolean or a quantitative signal that give us the value of satisfaction, a Boolean or quantitative value at each time. How it works, the monitoring algorithm? It works working on the parse tree of the formula. So given a formula, you can derive the parse tree of the formula, where at the bottom you have the atomic proposition and at the top you have the whole formula. From the atomic proposition, you derive the secondary signal. So you start with your trajectory, you compute you evaluate the atomic proposition and you compute the secondary signal, and from this you compute at each leaf of the tree, at each node you have a specific a specific operator that for which there is a specific algorithm. So each operator has a specific algorithm that you compute with respect to the Boolean or the quantitative signal, and then you derive the Boolean and quantitative signal for the next nodes. And then you go up on the tree of your formula until you reach the top where there is the global formula. So at the end you have, as I say, a Boolean signal for the Boolean semantics or a quantitative signal for the quantitative semantics. And then we say also that the whole trajectory satisfy the formula if the trajectory satisfy the formula at time 0. What we will see with our spatio-temporal logic is that we have to add some spatial operator on the logic, and furthermore, instead to have just a temporal trajectory that is a set of temporal signal, we will have a spatio-temporal trajectory. So we have to add also the space, and furthermore we have to see how shape this space. So we have also to define what is the spatial configuration. And as a solution, instead to have just the Boolean and quantitative signal, you will have also the space. And in that case, we will not have, as for the temporal case, like a zero position. So we will have a solution for each location.
We use a running example to describe the logic, that is the wireless sensor network. So as starting point, just think to have a number of sensors in the space that are distributed in some way and that can measure some values, as for example the level of temperature or the level of pollution. For the moment we think to have just the same type of sensor. So before describing the logic, we have to describe what are the input and the output of our monitoring procedure. So we are going to describe the spatial configuration and what are the trajectory and the signal. The spatial configuration that we consider is a discrete space described as a weighted direct graph. Indirect graphs can be treated as direct graph with a symmetric relation. The reason why we chose this kind of description of the space are mainly two. The first is that many applications that we consider as the bike sharing system, the smart cities and sensor network are naturally framed in a discrete spatial structure. The second one is even other kind of system as a continuous space is often described as a grid or as a mesh. Think, for example, the numerical integration of partial differential equation. So for that reason, now until now, the description of a space as a weighted graph seems to have the better description that we can have. So we define a space model as a tuple LW, where L is a set of nodes that we call location, and W is a proximity function that associates a label that is a real value to each distinct pair that are connected. So you can think to this W, capital W, just as a subset of the space location times real value times location, and you say that if there is a tuple, for example L1 W L2 that belongs to this set, so to capital W, it means that there is that L1 and L2 are connected and that there is a weight equal to W. As you can see here, for simplicity, we consider undirected graph. You can see there is an arrow going in both the direction. This is the same to say that there is an arrow going from L1 to L2 and another arrows that are going from L2 to L1, and both have a label equal to W. Okay. But usually when you write L1 W L2 means that there is an edge going from L1 to L2 with weight W. We can define different graphs on the same set of location. Here we can see an example with respect to the sensor network. This is the connectivity graph. And we say that two locations, so two sensors, are connected, so there is an edge, if and only if they are within their communication range. So each sensor has a specific radius that design a circle like around him, where if there are sensors that are within this circle, that they can communicate. So if two different sensors have their communication range that intersect, then they can communicate, and so there is an edge between them. Another example is the proximity graph, and this is the dual graph of the Voronoi diagram. The Voronoi diagram is a partition of the place into a number of regions, and you have one region per location. And in particular, it's assigned each point of the plane to the region corresponding to the closest location. Okay. So in the case of the proximity graph, if you have a really few sensor and the space is still very large, you can have very few regions here, but you will have always some connection between the sensor, even if their communication range is not intersect to each other. We defined then a route. A route is an infinite sequence of location. And the important characteristic of the route is, of course, that if for each pair of location in the sequence, there should be an edge. So you can see here two examples. So L0, the sequence L0, L1, L2, L1 is a root because as I say, we are using undirected graph, and here we can find an edge that goes from L0, L1, one from L1 to L2, one from L2 to L1, so we can go back. Instead, the sequence L0, L1, L2, L3 is not a root because there is no edge, no edges that goes from L2 to L3. And then just to know, we denote the IT nodes as tau I with the square bracket, and instead we define the first occurrence of a location in the root with instead the round bracket. So tau L is used to denote the first occurrence of L in the sequence tau. So just to understand, tau L in the sequence L0, L1, L2, L1 is equal to 1.
We can use routes to define the distance among two locations. And to do this, first we define a route distance, and then we define a distance between locations. So the distance is computed using an appropriate function f, and we will see some example later. And this function combines the different weights in the root into a value. So, and it's done in a recursive way. So you define a distance upon a certain index, and then actually you decrease the IT for at each iteration until you reach the I equal to 0. But we will see this in the next slides with an example. And just to know, so the distance on a route is defined with respect to the index. You can define the distance with respect to a specific location, and this corresponds to consider in the route the index that corresponds to the first time that this location is considered in the route. Let's see two examples of this function f that we can see here. One is the weight, that is just the sum of the inputs. So this corresponds just to sum the value of the label of the weight in each edge. And another possibility is, for example, the OPS, where you're not going to count to sum the value in the edge, but you're just summing one for each edge. So what you're going to doing here is to count the number of OPS that you have in the root. So let's see one example of computing the distance. So here we are computing the distance considering the weight function and up to the index 2. So you're going to compute the function weight, considering here is the value of the first age that goes from L0 to L1, that is 4. And here you are going to consider the distance of the root from the next step, so from L1, and decreasing by 1 the index, so from 1. Then here is just a sum, so you sum here, and here you are doing the same again. So here you are going to consider the value of the edge from L1 to L2, that is 2. And then you are going to decrease again from 1 to 0 the index, and you are going to consider the root not from L1 but now from L2. And then again you are going to sum them, and when we arrive to 0, the value of the distance is equal to 0. So you have 6. That is exactly the sum of the weight in the root. Similarly, if you do the same, consider the hope function, what you have at the end here is just 2, because you have summing 1 on 1 2 times, and that is exactly the number of hopes that you have in the root. Then you can define the location distance that correspond to what is the distance between two locations, that correspond to the minimum considering all possible routes that start from Li and goes and ending to Lj. So for example, taking the previous example, if we are going to see the location distance from L0 to L2, considering the hoped distance and all possible routes, in this case we have just the value equal to 2. But for example, if you add an edge that go directly from L0 to L2, then this value will be equal to 1. And finally, we define the signal and the trace. The signal is just a function that associates at each location a temporal signal, where D can be different things, can be a Boolean set, or can be the real value, or maybe can be also integer values. So you have a different possible signal, a Boolean signal, a quantitative signal, or an integer signal. And then we define the spatial temporal trace or trajectory as a vector of temporal signal. So for example, if you think again to the sensor network, the spatial temporal trajectory means to consider, for example, the value of the temperature in each location in time, and the value of the battery. Finally, as I said, we can consider both static and dynamic spatial configuration. So what we defined at the beginning was a static spatial model. But we will see also dynamic spatial model. In the dynamic spatial model, what you have is just a different possible space model at each time. So we will denote the dynamic spatial model just considering S as a function that will give at each time step t a specific spatial model Si. Since we will consider just constant piecewise constant signal, you consider to have the same space model until the next time step. And here we can see just an example of two different space model of the same sensor nectar system, where you can see that the spatial configuration, so the number of edge and the type of edge change in the two different time steps. Okay, now we are going to define the logic. The spatio-temporal reach and escape logic STREL is an extension of the signal-temporal logic with a number of spatial operators. Here we can see the syntax of STREL, where true is the Boolean true constant, mu are the atomic proposition, then we have negation conjunction, the temporal operator until and since, and then you have the spatial operator reach and escape. Then we can derive other operators, the disjuncture operator and the temporal operators eventually, globally, once and historically, and then the spatial operators somewhere, everywhere, and surround. To describe the spatial operators, let's consider a simple graph, as you can see here in the slide, where the color in the node correspond to an atomic proposition that is satisfied by that node. Means that we consider to focus only on spatial operators, we consider as atomic proposition colors. So like the yellow atomic proposition is satisfied by all the nodes that are yellow. And similarly, the blue proposition is satisfied by the nodes by the location that are blue, and so on. So in this way, we focus in understanding just the spatial operators. The first operator that we see is the reach operator. The property phi1 reach phi2 at the distance between d1 and d2, considering the function distance f, describe the behavior of reaching a location that satisfy the phi2 property, passing only through a location that satisfy phi1, and such that the distance from the initial location and the final one belongs to the interval d1, d2. A bit more formal, considering a spatial system S and a spatio-temporal trajectory X, we say that that system in location L at time t satisfy the reachability property if and only if it satisfies phi2 in a location L prime that is reachable from the location L through a route with a length that belongs to d1 and d2. The length that starts from L, and that we are considering the route from L to L prime, and all its elements with index less than tau L prime satisfy phi1. So we have a route that goes from L to L prime, and all index before L prime satisfy phi1, and the L prime, the route at index where there is L prime satisfy phi2. Let's see an example to better understand the operator. So here we have a graph, and we want to see if there are locations that satisfy the property yellow, rich, pink, in an interval between 1 and 4, considering the Hopf function. So to simplicity, in this example, we use just the hops function. So we are just considering the edge all with the weight all equal to 1, and not adding further like value to make the things simple. So let's see, for example, here we can see that the location, for example, L3 satisfy the property that yellow reach between 1 and 4, pink, because we can find a root, for example, L3, L13, L14, L17, L35, where the location L35 satisfy the pink property. All previous location of the root satisfy the yellow property, and the distance from L3 to L35 of this root is 4. So it's less than the upper bound of our interval of the interval distance. Instead, if you can see L4, so the location L4, so that one, does not satisfy the property, because the distance of the root of this root to L35 is 5. So it does not belong to the interval, and so the property is not satisfied. The escape operator, escape phi, at the distance between d1 and d2, considering the distance function f, describe the possibility of escaping from a certain region, passing only through a location that satisfies phi, via a route with a distance that belongs to the interval d1 and d2. So a spatial model S and a spatio-temporal trajectory X satisfy this escape property in location L at time t, if and only if there exists a root tau and a location L prime that belongs to the root, such that the first element of this root is L, and in the distance, the root distance between the location L and L prime belongs to the interval d1 and d2, and all elements in the root from the first element L to the element L prime satisfy phi. So let's understand better the operator with an example. We consider the property escape, the orange property, at a distance more than 3, considering the distance, the hop function. So we can see, for example, that the location 9 satisfy the property, and we can see together why. So we can see that there is a root L9, L10, L11, and L12 that as a first element, it has as first element L9, and there is an element that is L12, such that the distance between L9 and L12 is 3. 1, 2, 3. And all elements satisfy the orange property. Okay. We can see instead that, for example, L10 does not satisfy the property. Why? Because we cannot find any element such that the distance between L10 and this other location is more than 3, and all the elements satisfy the orange property. We can see that the maximum that we can have is a root with 2 at the distance of 2. So there is no elements at distance equal or greater than 3 where all the elements where there exists a root with this element, and all the elements satisfy the orange property. So these were the operators of the logic, and then we can of the basic operator, and then we see the operator that can be directly derived from these two operators. The first one is the somewhere operator, and the meaning is really simple. The meaning is that from a certain location, the property somewhere phi at the distance between d1 and d2 is satisfied if there exists an element at the distance between d1 and d2 from phi where the property is satisfied. So let's see this directly with an example. Somewhere pink at the distance between 3 and 5, considering the Hopf function, is satisfied, for example, by the element L1, because there is a location, the L35, that satisfies the pin property that is at the distance between 3 and 5, because we can see there is a root 1, 2, 3, 4 that permit us to arrive to reach P at the distance below that bit more than 3 and less than 5. Then we see the everywhere operators that instead to say that there exists a location at a certain distance from where I'm checking the property that satisfy the property phi, we say that all the location that belongs to the interval d1 and d2 must to satisfy the property phi. So a spatial model and a spatio-temporal trajectory satisfy the everywhere property if and only if in location L at time t, if and only if all the location L prime that are reachable from L via a path with a length that belongs to the interval d1 and d2 satisfy phi. So here we can see, for example, that L1 still satisfy even this property because all the elements that are at the distance between 2 and 3 satisfy the yellow property. And instead, for example, L2 does not satisfy the property because there is an element, a location, L18, where the distance is still less or equal to 3, but the property yellow is not satisfied. And finally, we see the surround operator. So phi1 surround phi2 at the distance d1 and d2, considering the distance function f, expresses the topological notion of being surrounded by a phi2 region while being in a phi1 region with some additional metric constraint that now we see more in detail. So the idea is that you have a phi1 region that is surrounded by a phi2 region. We say that a spatial model and a spatial-temporal trajectory satisfy the surround property in location L at time t if and only if there exists a phi1 region that contains L and all the locations in that region satisfy phi1 and are reachable from L via a path with length less than d2. And so in this way we describe the phi1 region. And then we say that all the locations that do not belong to this phi1 region but that are directly connected to a location in that region must satisfy phi2. And we have then the distance, the metric constraint that say that all these locations that are directly connected with some location that belongs to phi1 must be reached from L via a path with length in the interval d1 and d2. So what's the idea is that all the elements that belongs to the feature region are anyway inside the ring d1 and d2 as a distance from the location that where we are checking the property, that is L. So let's see also this one with an example that can help to clarify the operator. So we consider in the property green surround blue at the distance between 0 and 100 with considering the hope function. And we can see that in that case all green points satisfy this property. Why? Because for each green point we can find a region that contains that point such that all its points are green and all the points connected with an element that belongs to that region are blue and satisfy the metric constraint. Why? Let's, for example, consider this location 47. So we have a region that is the green region where all the elements are at the distance between 0 and are at a distance less than 100 from the location L47 for sure. And then we can see that all the location that does not belongs to the green location, the green region, but that are directly connected with that region, they are blue. And for sure they are at the distance that is more than 0 and less than 100. To better understand the distance constraint, let's see the same property but with a different distance interval. So instead of 0, 100, we have 2 and 3. In that case, the only location that satisfies that property is the location in the center, so the location 43, because it's the only one for which there exists a region, the green region, where all the elements satisfy the green property and they are at the distance less than 3 from the location 43. And all the elements of the blue region, so the ones that are directly connected to the green region, are at a distance between 2 and 3 from the location that 43. All the other are the distance has some element at a greater or smaller distance. With this we finish the first part of the tutorial and we will see later for the second part.